Hello students, this is your professor Dr. Mink. Welcome to the audio lecture for Chapter 2. Please remember the protocol for reviewing these audio lectures, and that is you should have read Chapter 2 before reviewing this lecture. I'm not saying this to give you busy work. I'm saying this because that is the way that this learning process is structured. You're obviously in an online or a hybrid class, which is why you're reviewing an audio lecture as opposed to having me interactively or synchronously in the classroom to ask questions and to contemplate issues that you might have with certain concepts presented. That is not the case in an online or, in some cases, a hybrid course. So please read the textbook before reviewing this lecture. With that said, let's go. In this chapter, we're really starting to get into programming. It should be a lot of fun. In Chapter 2, we will cover variables and assignments, input and output, data types and expressions, simple flow of control, and program style. This is a lot for us to cover, and I'm breaking up Chapter 2 into 2 lectures that in most classes we will cover over a 2-week period. The first major topic we'll cover is variables and assignments. In order to pass data in and out of a program, you need to have variables. Variables and assigning values to those variables is one of the hallmarks of any programming language. Variables hold values. They're like a small blackboard. I kind of like this analogy. We can write a number on them, and then we can erase and change the number, or we can just erase the number and leave it blank. C++ variables are names for memory locations, locations that hold data. We can store a value in them. We can change the value stored there. However, we cannot erase the memory location. Some value is always there. Let's take a look at display 2.1.
Okay, students, it's time for a short demonstration. I have in front of me a template for a program that has all of the startup statements, the declaration or the definition of our main function, its scope, the return 0, and you could write this program on your own and then save it as a template and just paste it into a new project each time we're going to start. But today we're going to talk about variables, and let's just put a section header to declare some variables. And let's declare 3 integers. So we're going to use the keyword int, and I'm going to call it int 1, int 2, int 3, and we'll call one sum. Okay? So that is how we declare 4 integer variables. We could also initialize one of those variables in the declaration statement. So I could also say, sum equals 0. At this point in time, we have 3 ints integers, int1, int2, and int3 declared, which means the space has been set aside for them, but there's no value in the space. And we have a fourth variable, sum, that has been declared and initialized. So then let's initialize the three declared but not yet initialized variables with input from the user. So let's prompt the user to enter data. Okay, this is a comment. So now I'm going to use cout, an output statement with the insertion operator. We're going to insert a string. Enter 3 whole numbers. And I'm going to put, whoops, and I'm going to end that with a semicolon. Okay, this is an output prompt. And then cin, extraction operator, the opposite of cout, and then we're going to put the variable that will receive the first whole number entered. The second one, whoops, I'm sorry, int2, int3. So this will initialize those three variables. And then we'll do an assignment statement. Sum equals int1 plus int2 plus, okay, what we have, whoops, semicolon. I have a new keyboard. I have actually a new computer, so keyboard's a little bit different than the laptop I had before. So what we have on the right hand side of the assignment statement is an expression that will be evaluated and then assigned, the equals is the assignment statement, be assigned to sum. So we are assigning an expression to sum. And then let's output. Let's output the results. Now watch this. I'm going to send a string, the sum of, now watch this, whatever's in int1. Then I'm going to put another string, plus, another insertion operator, int2, another insertion operator, plus int2 plus int3, this is a string, equals, and then I'm going to put an end line so the cursor winds up on the next line. Notice we have extra spaces, things like this. So now I'm going to save this, go up to local Windows debugger, and we'll run this. Enter 3 whole numbers. I'm going to say 2, 5, and 8. And that should be 15. There we go.
Students, here we have a sample program, and you see the include statement using namespace standard and int main, which is the code we put at the beginning of a program. We'll get into that in more detail. And then you see, after the open bracket, the first two lines of programming statement, and they're in a light blue color on this slide, are declarations of variables, variable names. The first line, in number of bars, we're setting aside a location, a memory, a variable called number of bars that will store integer numbers, whole numbers. The second line in that sequence, double, one weight, comma, total weight, we're declaring two variable names, one weight and a second total weight, that will hold double variables. And we'll get to doubles later. Double is a number with a fractional component. 1.75 would be a good example. And these variable names are used then to accept input. See the cin statement, which is also blue? Cin number of bars. There, the user of the program enters a number, so it might be 10 number of bars, and then they're entering one weight using cin, and then cin number of bars later. That allows, the cin statement allows the user to enter a value that gets assigned to the number of bars variable and held within the program so that number of bars can be used for further calculation. Very important concept. In the next slide, we'll take a look at the dialogue of this program when it runs. Here is a sample dialogue from that program on the previous slide running. And you may want to stop and back up one slide and take a look at it and then come back to this so you understand what's going on. But the cout statements prompt the user, enter the number of candy bars in a package and the weight in ounces of one candy bar, then press enter. Those first three lines of output were generated using the cout statement, which you'll see on the previous slide. Then the values in bold, 11 space 2.1, are the number of candy bars in a package and the weight in ounces of one candy bar. Those are entered as input, and enter is pressed after 2.1, and those two values get assigned to those variables using the cin statements. And then there's more cout statements from the program, and then the program prompts to try another brand. This is a cout statement, output, and then it goes back into the program again, enter the number of candy bars in a package and the weight in ounces of one candy bar, then press enter, and then through cin, the user enters 12 and 1.8, and the program runs again and generates the output after that input. Please stop and take a close look at this, then back up one slide, take a look at the program, come back and forth. This is a critical crossroads in this learning process. cin and cout, how to get input into a program and output from a program, and assignment of values to variables after they've been declared. I hope this was useful. Let's move forward. Variable names are called identifiers. And when you're choosing variable names, and you, the programmer, have total control over the selection of variable names. There's not a list of acceptable variable names that you can choose. But you want to use meaningful names that clearly represent the data to be stored, because although you may write a program, and that program may go into production after it's debugged and tested, someone may come back a year later, 2 years later, and have to change or modify the program because the requirements have changed, and you want the program to be easy to read and understandable and intuitive. Some rules for naming identifiers: the first character must be a letter or the underscore character, and the remaining characters must be letters, numbers, or underscore characters. No special characters, exclamation points, question marks, etc., etc., etc. So if I were creating a variable for the number of bars, a variable that would hold the value of number of bars in the program, I'd use number underscore of underscore bars, or just simply number underscore bars. Your identifiers, your variable names, have to or cannot match any of the keywords of the C++ programming language. These are called reserved keywords, and the standard reserved keywords are, and here's a list of them. I'm not going to read them off to you. If you use one of the standard reserved keywords, you'll get an error, and you'll have to change that, and it's no big deal. Here are some other alternatives that cannot be used as identifiers. These are operators, and one of the things I want to make sure you understand, a very important point, C++ is a case-sensitive language. So, as the author keenly notes here, the result, all in caps, variable is not the same as result, all lowercase, or result, capital R, lowercase esult. These are three totally different variables, and they might as well be named George, Mary, and John, because the computer does not recognize any similarity between those three. Okay, here the author's really beating a dead horse. Keywords, also called reserve words, must be used as they are defined in the programming language and cannot be used as identifiers. I think that's what we've been saying for the past few slides. But anyway, there you go. Before a variable can be used in a program, for example, before you use that cin number of bars to load the input from the keyboard into the variable to store the number of bars, the variable must be declared. And this declaration statement, which you saw at the beginning in number of bars, tells the computer the type of data to store in the variable. And here's the example I just mentioned. In number of bars is a variable that will store only integer numbers. So if I try to put 55.7 into number of bars, it will be truncated to 55, which is not a good thing. Double, one weight, total weight will hold numbers with fractional components. Here's some more. Int is an abbreviation for integer, stores whole numbers, 3, 102. It also stores negative numbers, minus 456, etc. Double represents number with a fractional component. It could store 1.34, minus 345.6, etc. And in the program we just looked at, the double variables declared were one weight and total weight. As I mentioned earlier, variables have to be declared before they are used. And here are two examples of locations for variable declarations. You can declare them immediately prior to use, which is not my preference. So here's an example. You have the main program, and you might have 20 lines of code before you're going to sum score 1 and score 2 and assign those existing variable values to sum. And right before, in the line before, you might declare the integer sum. Okay. Or, my choice of preference, at the beginning of the program, declare all your variables that are local to main. And we'll talk about that later. But for the beginning of this course, We're not going to have any function definitions, declarations, etc. Functions that return values. We will get to that later. So everything will be programmed in the main program, and you want to declare your variables at the beginning of the program. It is the safest way. This slide shows the syntax for declaring variables. First, you give it the type name, double, int, float, bool, char. We'll get to those others later. And then the first variable name. If you're only declaring one variable of that type, then you put semicolon. If you want to declare multiple variable names, set aside multiple locations to hold data of that type, integer, float, double, etc. You put a comma, then you put the second variable name, comma, etc. You could put 50 on one line if you felt so inclined. Here's some examples, declaration examples. Here we're defining 3 doubles in the first line. Double, average, comma. That's one. Double variable of type double. Then m underscore score and total score. On the second line, you're declaring just one double called moon distance. On the third line, you're declaring 2 integer variables, age and num students. And on the fourth line, you're declaring 1 integer variable called cars waiting. I hope this is clear to you. If not, let me know. An assignment statement allows you to change the value stored in a variable. An example of an assignment statement is total weight equals 1 weight plus number of bars, semicolon. Let's dissect this. We're assigning the result of adding the value stored in 1 weight plus the value stored in number of bars. We're assigning that result of that addition to total weight. So the assignment goes right to left. We're assigning what happens on the right to the variable on the left. Total weight is set to the sum 1 weight plus number of bars. So if 1 weight was 10 and number of bars was 15, total weight would be 25. Assignment statements end with a semicolon, and the single variable to be changed is always on the left of the assignment operator. The equal sign is the assignment operator. On the right of the assignment operator, you could have constants such as age equals 21, variables, or expressions. We saw an expression at the beginning of this slide. Here's another expression. Circumference, the variable circumference, is being assigned diameter times, that's an approximation of pi, 3.14159. As we're talking about assignment statements, I want to be clear with this concept. The equals operator, the equal sign operator in C++ is not an equal sign. So the following statement cannot be true in algebra. Number of bars equals number of bars plus 3. However, in C++, it means the new value of number of bars is the previous value of number of bars plus 3. So if number of bars before this program statement is executed is 7, after number of bars will be 7 plus 3, or 10. When you declare a variable, you don't give it a value. Well, up until now, we haven't given a variable a value in the declaration statement. Giving a variable its first value is called initializing the variable. Variables are initialized in assignment statements. So here's an example of a variable, a double variable named MPG, being declared double MPG, semicolon, and then immediately in the next program statement, program line, being initialized with the value 26.3. 26.3 is being assigned MPG. Now, of course, MPG has to have been declared before you can assign a variable to it. I'm sorry, a value to it. Declaration and initialization can be combined using two different methods. Method number one, during the declaration statement, you can put an equal sign and then the initial value, such as described in method 1. Double MPG equals 26.3, comma, area equals 0.0, comma, volume. This declares and initializes two doubles, MPG and area, giving them 26.3 and 0 respectively. And it also declares a third double, volume, but gives it no initialized, it doesn't initialize it. The second method, same results, is to put the initial value in parentheses after the declaration. Double MPG and then 26.3, area 0.0. Those two lines in method 1 and method 2 yield the exact same results.
We have time for one last demo before we depart this section on declaring and initialized variables. This is a simpler version of the code we looked at a few slides back. And I've got a section here where I'm declaring a couple variables. I'm declaring three integers, int1, int2, and sum. And then I'm going to prompt the user to enter two whole numbers. And then I'm going to initialize two variables via keyboard input. So we're going to solicit two integers using the object cin from the keyboard. We're going to extract those values and store them in int1 and int2, and thus int1 and int2 will be initialized. Then sum gets initialized via an assignment statement. We're going to take the value in int1, add it to int2. This is an expression in the parentheses, and we're going to assign that to sum. Now I'm going to show you something that's really useful. I'm going to come over here and I'm going to left click one time. That puts a breakpoint. And when we're in debug mode up here, we could use breakpoints to debug our code and see the memory. I'm going to put a breakpoint on that line. Then I'm going to put a breakpoint on line 13. So here we are, and look at the memory down here. We have our locals window. int1, int2, and sum have these weird, I wish they were X's or question marks, but that is a value that is used for undefined. Don't ask me why. It's not the way I would have done it, but anyway. This means they're declared, but they don't have a value in them yet. In other words, they've not been initialized. Now I'm going to come up here, and when I hit a breakpoint, it opens the debug menu, and I could show the next statement. I could step into, step over, step out of. We're only going to use step over for now. I'm going to step over this cin statement, and you'll see that prompts us to enter two numbers. I'm going to say 3 and 8. Press enter. Now let's come back here and look at int1 has been initialized. It holds 3. int2 holds 8. I'm dragging this around so I have enough space. So now we're at a breakpoint. We haven't yet executed line 13. I'm going to step over that and look. Now that I've stepped over that, sum has a value. It's 3 plus 8. And if I step over one more time and display our output, our console, there it is. The sum of int1, insert that string, int2, insert that string, sum, and then an end line, and it puts the cursor down here. If I hit continue, it'll just end, and it will ask to press a key to close the console window. And I hope this is helpful in you understanding declaration of a variable, which sets aside space in memory, empty space, doesn't have anything in it, and then initializing that variable means to store an initial value in the variable location in memory. And obviously that can be changed over and over again.
That completes the content for section 2.1, and as a conclusion, I'd like you to try these individual projects on your own. When I deliver this lecture in class, in a traditional, non-hybrid, non-online class, we do this together in the class. Can you declare and initialize two integer variables to 0? The variables are named feet and inches. Try that. If you have any problems, contact me. Declare and initialize two variables, one int and one double. Both should be initialized to the appropriate form of 5. And can you give good variable names for identifiers to store the speed of an automobile, an hourly pay rate, the highest score on an exam? There are no exact correct answers for that last one. Speed of an automobile could be auto underscore speed, it could be car underscore speed, it could be speed underscore, but they need to be intuitive and they need to be clear as to their intent. Next section covered is input and output. Now that we've learned how to declare a variable that will store values, we often want to give the user the opportunity to input the initial value of those variables. We prompt the user with an output statement from cout, and then we accept the input with the input statement cin. And we'll drill down on those two concepts, the primary input-output methods for C++ in this chapter. A data stream is a sequence of data, typically in the form of characters or numbers. An input stream is data for the program to use. Typically originates at the keyboard. We're going to do this for the first almost half of this course, and then I will show you file stream objects, how we can use or generate or create input for a program in a file, so you don't have to type it in through the keyboard. It is read in through a file. An output stream is the program's output. The destination is typically, and for the first half of this class, it will be the monitor. However, as we get into file streams, I'll show you how to send output also or just to a file. You can send output to the monitor and a file, the monitor, or just a file. We're going to generate output using the cout statement. Cout is an output stream that sends data to the monitor. The insertion operator inserts data into cout. So here's an example program statement. If I want to send output to the monitor that includes the value stored in the variable number of bars, followed by a space and the literal text candy bars ending with a new line, I use this cout statement. Cout, then the insertion operator pointing to the left, then the name of the variable whose value will be output, then another insertion operator, and then the literal, this is quoted with the double quotes, space candy bars. Please note, if we didn't put the space in front of candy bars and the value stored in number of bars was 10, you'd have 10, and then you'd have the word candy bars butted up against it with no space. Here are some examples using the cout statement. This first two-line example produces the exact same results as the previous sample. Cout, insertion operator, number of bars, semicolon. Because we didn't add a new line at the end of that cout statement, the next cout will begin on the same line. Cout, we've got the double quote, the space, and then candy bars. That will output the value stored in number of bars, followed by space, candy bars, and then a new line. Here's arithmetic performed in the cout statement. Cout, insertion operator, quote, double cost is $. Notice no space. Then insertion operator, the variable price plus tax. So whatever, let's say price is $10 and tax is 7 cents, that will come out to 10.07. And this will output total cost is space, $, no space, 10.07. Quoted strings are enclosed in double quotes, as you've noted before. Don't use two single quotes. A blank space can also be inserted with putting a space between two double quotes. If there are no strings in which a space is desired, as in space candy bar, /n, or \n. When you're using functions like cin and cout, you have to add an include directive to the beginning of the program, which includes, it adds library files to our programs. It tells the compiler and the linker where to find the definitions, the program definitions of the functions being used. Cin and cout are part of the IOStream library. So to make the definitions of cout and cout available to cin and cout available to the program, we put the include directive, #include IOStream. Using directives use directives to include a collection of defined names to make the names cin and cout available to our program. We also use namespace standard, which I touched upon in the Chapter 1 lecture. That keeps us from having to put standard : in front of each instance of cin or cout. Escape sequences tell the computer, or tell the compiler, to treat characters in a special way. The / is the escape character. You'll see it right above, well, on my keyboard, it's right above the enter key. I'm on a laptop, and I think that's rather standard. So to create a new line in output, use escape n. And it has to be in quotes. Or there is a newer alternative to create a new line, and that is cout, insertion operator, ENDL. I use both. Other escape sequences, if you want to put a tab, escape T. If you want to put a / character, you have to escape and then / or a quote character to be output literally. You put an escape and then the quote, because they have special meaning by themselves. Real numbers, which are type double, can produce a variety of results. Here's an example. Double price equals 78.5, and then cout, the literal, the price is $, space, and then price and L. The output could be any one of these, 78.5, 78.500000, etc., etc., etc. The most unlikely output is the one we really wanted, which is 78.5. Don't panic. There is a way to control the exact output of real numbers, and I'll show you in the next slide. Cout includes specific tools or program statements to control the output of double variables. And here they are. They're the setF statements. To specify fixed point notation, where there's a decimal point in between the whole and fractional component, you insert setF ios : fixed, that statement right there. To specify that the decimal point will always be shown, you execute or insert that setF statement, the show point statement. To specify that 2 decimal places will always be shown, you insert the precision statement with a 2. So, for example, to get the output the way we wanted it, you just put these 3 lines of code in before the cout statement, and they will control fixed point, show the decimal place, and how many decimal places will be shown. Cin is an input stream that brings data in from the keyboard. It allows input from the user of the program into the program. The extraction operator removes data to be used. Here are some examples. Cin is almost always used after cout. Cout prompts or sends output to the screen telling the user what type of input they should enter, and then Cin receives the entered input. So here's an example. Cout, enter the number of bars in a package, new line. Cout, and the weight in ounces of 1 bar, new line. And then the Cin statement would accept the number of bars and 1 weight. The code prompts the user to enter the data, then reads 2 data items from Cin. The first value read is stored in number of bars. The second value read is stored in 1 weight. And the data is just separated by spaces when entered, white space. When using Cin, you can read in multiple data items, and you're separated by spaces. The data, all the data on a line is not read in until the Enter key is pressed. This allows the user to make corrections. So if you prompt them to type in 3 initial values for variables v1, v2, and v3, and they want to type in 10, 15, and 20, and they type in 10 space 15 space 20, and they realized instead of 15 they actually typed in 51, they transposed them, but they didn't hit Enter yet. They can backspace to the 51 and change it to 15 space 20, then hit Enter. You always want to prompt the user for input that is desired, and you prompt the user with cout statements. So here's an example on this slide where you want to have the user enter a value for age, the variable age. And I'm assuming that would be an integer. Before the Cin statement that allows you to read in age from the keyboard, you put a cout statement, enter your age. Notice at the end of the enter your age there's a colon and a space, but no end line. That means enter your age is going to be sitting there, and on the same line they could type in age and hit Enter. Another common practice is to give the user a chance to verify the data. So after they've entered age and press the Enter key, you can immediately cout age quote space was entered. And if they entered the age 21, that line will say 21 was entered.
Let's take a quick visit back to our demonstration we were working on earlier in this lecture to emphasize how C-in and C-out work and how we prompt the user to enter input on the same line as the prompt. Notice line 10, C-out, and then I'm outputting the string, double quotes, enter two whole numbers, colon, space. And I've got a breakpoint after that. So notice where the cursor is. So right now if I start entering if I proceed past that breakpoint, enter 1, space 2, I'm on the same line. And then I can continue. The sum of 1 plus 2 equals 3. And that comes from, this right here. Now let's try it again with an end line. This example, enter two whole numbers and look where the cursor is, because the end line, which is a carriage return, put us in the next line. So if I just finish running this, proceed past the breakpoint, if I enter 1 and 6, there we go. I hope this demo was useful.
This concludes section 2.2. Here are some tasks and questions you should be able to perform and answer. I have put a solution on the next slide. Take a look at these and see if you can write an input statement to place a value in the variable the number. Write the output statement to prompt for the value to store in the number. Write an output statement that produces a new line. And format output of rational numbers to show 4 decimal places. Think about these before you go to the next slide. You could even try them if you'd want. And I have a solution for you on the next slide, and then we'll move forward. Here is the solution for the items on the previous slide. You see the setf statement for fixed point, show the decimal point, and set the precision at 4. And we're declaring a double, the number. Then the cout statement, enter the value for the number. Cin, the number. Cout, you entered the number. New line. The system pause, I'll explain that further. That just allows you to see the output. I would like you to put this into the compiler, into the editor, and compile it and run it and see the output. It would be very useful to you. I've given this to you. You can copy and paste it right from this slide. Give it a shot. We're now going to cover section 2.3 of your textbook, data types and expressions. Every variable that you declare has a specific data type, and expressions are used on the right-hand side of many assignment statements. And we'll get into it right now. This slide begins describing the differences between an integer and a double. Integer numbers, such as 1, 2, 3, 7, 582, are stored as their exact values. Doubles may be stored as approximate values due to limitations on the number of significant digits. You understand that 1/3 in decimal actually goes 0.33333 almost to infinity. No, I think to infinity. So at some point in time there's going to be an approximation. A whole number such as 2 is stored as an int, int. 2.0 is stored, well, has to be stored as a type double because it has a fractional component. As I mentioned in the slide before and previously, an int does not contain a decimal point. It is a whole number. Here's some examples of int or integers: 34, 45, 1, 89, 7,263 are all integer numbers. They contain no fractional component and they are exact. Doubles can be represented two different ways: fixed point or floating point using fixed point or floating point notation. Fixed point is the most common format, and it includes a decimal point. Examples: 34.1, 23.0034, 1.0, 89.9, etc. Floating point notation, also known as scientific notation, is represented differently. 3.41 E1 means 3.41 times 10 to the first, or 34.1. 3.67 E17 means 3.67 times 10 to the 17th, which equates to that long number. I'm not going to even try to say all those zeros because I'll probably make a mistake and I'm being recorded. Never let yourself be recorded making a mistake. 5.89 e to the minus 6 means 5.89 times 10 to the negative 6th, which equates to that number, 0.0000589. There, I think I got that correct. The number to the left of E does not require a decimal point. Exponent cannot contain a decimal point. Floating point notation it's used, but it's rarely used. I can tell you it's been a handful of times in the 20-some years, 25 years since I've started programming, almost 30. Oh my God, I'm old. Yeah, it's been 30 years since I took my first programming class, and I've not used scientific notation all that much. The various number types have different memory requirements. More precision requires more bytes of memory, and we'll show you a slide next that quantifies the number of bytes for each different type of number we're going to store. But very large numbers require more bytes of memory, and very small numbers require more bytes of memory. So you're thinking, well, why not set everything as a double and just be done with it? Well, think of the initial code written for Facebook, which probably was planned for, I don't know, 1,000 users. I think it was at Harvard University. And if the memory allocation for every, for every variable was a double, instead of an int when it needed to be an int, instead of a float when it could have been a float, you're talking about a matter of 4 times, in some cases 4 times, the resources needed to process the code. Now Facebook has, last time I checked, close to 1 billion users, and the code, which might have been planned for 1,000 users, is now being processed millions, if not trillions of times every day. And the overhead, the memory and storage necessary for that code goes up exponentially. So think about the efficiency of your program, and you want to use the smallest allocation of memory for a variable that you'll reasonably need. Let's take a look at the next slide, and you'll get a better idea of the point I'm trying to make. This slide shows the amount of memory required to store various data types. Short being the smallest, 2 bytes, 8 bits in a byte, so you're really talking about 16 bits in 2 bytes. An int requires 4 bytes. And look at the size range of numbers that can be represented with an int. It's massive. Look at the float. We don't use long. Long and int are the same. I never really understood that. Float, 10 to the 38th. That is a massive number. So if you can use a float instead of a double, you half the memory allocation and the processing, the resources necessary to crunch those numbers. And then you have a long double, which is for astronomically large numbers. So you want to be conscious about writing a program, especially if some of you I know are computer science majors, and you might start working for a large corporation that has massive processing requirements. My first programming job back in the 1980s, I was working on a database that had over 4 million records in it, and that was in probably 1987. So these things happen. People do use computers, and they write programs for massive processing tasks. So you want to be as efficient as you can, and you wouldn't use a double when a float would be more than you would ever require. And you might use a short instead of an int if you're dealing with numbers in that small range. Integer or long int is 4 bytes. Equivalent forms to declare very large integers: long, big total, long int, big total. Short or short int, which is 2 bytes, short small or short int, small total. Here's some other declarations of a long double, which requires 10 bytes, as opposed to a double, which requires 8 bytes, and a float, which requires 4 bytes. I like the author's name of the float. Float, not so big number. That's deceiving, because a float can represent a significantly large number, as we noted on the slide. Not the slide before the previous slide. Computers also process character data. Char, which is short for character, is a data type that holds any single character from the keyboard. Very often used, type Y for yes, N for no, to continue with the program. Very, very common. Here's an example to declare a variable of type char, named letter, just simply char letter, semicolon, and that stores one character. Could be an A, could be an R, could be an S, could be a P, could be a Y, could be an N. You can also initialize a char when you're declaring it. And here's an example. We're setting up a memory location to hold a char. Its identifier is letter, and we are initializing it to the letter A. Notice character constants are enclosed in single quotes. Strings, which are multiple characters, are in double quotes. So double quote A is a string of characters containing one character. Single quote A is a value of type character. More on this later, I promise. cin skips blanks and line breaks when looking for data. The following code is used to read two characters, but skips any space that might be between them. So first we declare two chars, symbol 1 and symbol 2. Then you use cin to extract symbol 1 from the keyboard and symbol 2. So the user typically separates date items with spaces. So the user might type in J space D, enter, and J would be assigned to symbol 1, D would be assigned to symbol 2 using cin, but the results are the same if the data is not separated by spaces. You can type in J and D, J, no space, D, enter, and it will still assign J to symbol and D to symbol 1 and D to symbol 2. Here's a program, 2.3, that, and this is from the textbook, that illustrates how chars are declared and then input using cin. So we declare three chars, symbol 1, symbol 2, and symbol 3. We use cout to prompt the user to enter two initials without any periods, new line, and then we use cin, symbol 1, symbol 2 with the insertion operator. Then we use cout to verify the two initials are, new line, and then we use cout, symbol 1, symbol 2. And then cout once more with a space, because remember the first cout, symbol 1, symbol 2, end line, is going to butt those two initials right next to each other. So then, cout once more with a space. We initialize symbol 3 as a space. It's a single char. So you've got the single quotes. Now, cout, symbol 1, symbol 3, symbol 2. If you look at the output, the initial output, the two initials are J and B, right next to each other because we use cout, symbol 1, and then symbol 2, no spaces. And then the second output was actually symbol 1, which was J, symbol 3, which is the space between J and B, and symbol 2, which is the B. Hope this makes sense. You can download this program from the timeline. I gave you the source code. You can compile it and run it and play around with it. It's very useful, part of the learning process, experimenting with these programs. Thanks. Let's move forward. We're going to briefly touch on the type string, which is a class. It's different from the primitive data types discussed so far. And we'll discuss the string class in detail later in Chapter 8. You use double quotes around a string of text to store it into the string variable. And if you're going to use strings, if you're going to declare and use strings, you have to include the include directive for this string class library, and that is #include string, as you see it there. To declare a variable of type string, once the include statement is added, string, name, and then double quotes, and all of that name, can you pronounce that name? I can't. I'm sure it's long and complex just to make a point, but that entire name could be added to one variable that is of type string. This is program 2.4, and it demonstrates how to use strings. Notice it has the include directive for the string class library. We go right into the main program and declare three strings: middle name, pet name, and alter ego name. Not sure why we wouldn't have declared those all three of those on one line, but that works. Cout, prompt the user to enter your middle name and the name of your pet, and a new line. CIN is used to extract the value type for middle name from the keyboard and pet name from the keyboard. Then alter ego name is assigned pet name plus the string, notice double quotes, one space, plus middle name. So the value in pet name plus a space plus middle name are all concatenated, added together, and assigned to alter ego name. Then we have a cout statement. The name of your alter ego is space, and then cout alter ego name. Notice we're also adding a period as a string and an end line statement. And you see two sample dialogues from running this program. Enter your middle name and the name of your pet. That's cout prompts. The user enters what's in bold, Parker as his or her middle name, and Pippin as his or her pet name, and then the name of your alter ego is, that's the cout statement, and then actually output the value in alter ego name, which was pet name plus space plus middle name. Same thing. Notice in the sample dialog 2, enter your middle name and the name of your pet, enters Parker, and then enters Mr. period space Bojangles. Now, because there's a space, CIN never gets to Bojangles. It ends as the pet name being MR period. So the name of your alter ego is Mr. You want to be careful to store values correctly in the correct variable type. The example given here is what's called a type mismatch. We declare an integer called int variable, and then we assign 2.99 to int variable. Now, you might be thinking, well, ints are whole numbers, so that'll probably round that off to 3. It won't. It will truncate everything to the right of the 2, because it only accepts whole numbers, and it will most likely store the value 2, which is totally incorrect. This slide illustrates another example of a type mismatch. We declare an integer variable called int variable, a double called double variable. We initialize the double variable with the value 2.00. All good so far. Here's the problem. Then we assign the int variable the value in the double variable. If this doesn't throw a compiler error, int variable contains 2, not 2.0. It cannot, an integer variable cannot contain 2.00. The inverse typically works, though. It's not good form, but it does work. So in this example, we initialize a double variable called double variable, no pun intended, and then, we declare a double variable, and then we assign an initial value of 2. That double variable will actually contain 2.0. Here's some other examples of situations which they're possible but not recommended. It is possible to store char vals in integer variables, and here's how you do it. Int value, and you store the char a. The value will contain an integer representing a. It's also possible to store int values in char variables. Here's an example. Char letter equals 65. Not recommended though. Once more, here are some actions, assignments that are possible, but generally not recommended. Bool variables, bool values can be assigned to int variables. True is stored as 1, false is stored as 0. Remember, a bool is either true or false. Values of type int can be assigned to bool variables. Any non-zero integer is stored as true, and 0 is stored as false. Once again, these are possible, but they're just not examples of good practice. Arithmetic is performed with operators. These are common operators. They're used in Excel and most other computer programs. Plus for addition, minus for subtraction, the asterisk for multiplication, and the / for division. So an example of storing a product in the variable total weight using an arithmetic expression. Total weight equals 1 weight times the number of bars. So that would be the weight of 1 bar would be stored in the variable 1 weight, and number of bars would be an integer. So total weight most likely is a double or a float, because 1 weight is probably not a whole number. Arithmetic operators can be used with any numeric type. An operand is a number or variable used by the operator. It could be a number that's hard-coded into an expression, or a variable that holds a numeric value. Result of an operator depends on the types of operands in the expression. If both operands are int, the result is an int. If one or both operands are double, the result is a double. This can get tricky, and almost every class I've ever taught, students have gotten tripped up by this particular nuance of C++. And we're going to talk about this in great length moving forward. Let's drill down on this issue. This slide explores division of doubles. Division with at least one operator, which is a double, produces the expected results. Here's an example. We declare 3 doubles: divisor, dividend, and quotient. Divisor equals 3, dividend equals 5, quotient equals dividend divided by divisor. Quotient will hold 1.6666. Result is the same if either dividend or divisor is an int. Where you run into a problem is if the dividend and the divisor are ints and you're expecting a double. And just hold on to your seat. We're going to talk about that in great length. Here's the problem I was alluding to earlier. Integer division does not round the result. The fractional part is truncated. It's just removed. So you want to be careful with the division operator. An int divided by an int produces an integer result. Even if and in most cases when you're dividing, you don't get a true integer. So let's take a look at this example. We declare 3 ints: dividend, divisor, and quotient. Dividend is initialized to the value of 5. That's okay. Divisor is initialized to the value of 3. That's okay. And then quotient is assigned the result of the expression dividend divided by divisor. Well, 5 divided by 3 is not going to yield an int. The true result is 1.6666. However, the value of quotient becomes 1. It doesn't round up. It doesn't do any type of approximation that is going to help you. It just truncates everything off because it's integer division. And this is something you need to be aware of. It is often a problem. And we're going to talk a little later about typecasting and methods to get the correct result that you're looking for.
I set up this short demonstration to illustrate the integer division phenomenon. Let me walk you through it. We're declaring two integer variables named numerator and denominator. Then we're prompting the user via cout to enter two whole numbers for division, the numerator followed by the denominator. Then we use cin to initialize numerator and denominator with input from the keyboard. Then we're going to output the entire arithmetic expression. Cout the value stored in numerator. We'll add a string to the output stream that is space / space, then the value stored in denominator. Then we'll insert space equals space, and then the actual arithmetic operation, the expression numerator divided by denominator, and an end line. Now watch what happens when I enter 1 and 3, which is 1/3, which comes out to 0.3333, etc. One space 3, 0. Let's try it again. Let's try 1/2. 1 divided by 2, 0. Let's try 3 divided by 2, which would be 1.5. 1. Why is this happening? Whenever you have an integer divided by an integer, this expression is resolved before anything else happens. Numerator divided by denominator, int divided by an int, it cannot hold anything but the whole number component. So that resolves 1 divided by 3, 0. It sees the point, it can't hold it. It returns an integer. Let's try another iteration of this. Okay, so we've got a variable called quotient, and let's say quotient equals, and we're just going to take this expression and initialize quotient as numerator divided by denominator, and then we'll replace this with quotient. How many of you think this will solve the problem? Put a breakpoint here. 1 space 3. Now look at the memory. Quotient equals 0.000. Why? Because when evaluating an assignment statement, the right-hand side is evaluated first. Int divided by an int, 1 divided by 3, that returns an int, so we ignore the fractional component, so it returns 0. 0 then gets assigned to quotient. Quotient is a float, so it will be stored as 0.0, not 0.333. This is called integer division. And how do you fix this? Well, it's real simple. And we're going to cover this in more detail later, but it's only when you have an integer divided by an integer that the expression returns an integer. If this were a float, Were this were a float divided by an int returns a float, int divided by a float returns a float, float divided by a float obviously returns a float. So we can temporarily cast either the numerator or the denominator to a float. And I'm just going to do it this way. Now this is kind of advanced for where we are now, but what this will do is we'll take the numerator. Let's say we enter 1 and 3 again. It will make the numerator 1.0. It will cast it temporarily to a float. And watch. One space 3. Now look at the value stored in quotient. There it is. And if I continue, problem is solved. This is a problem that haunts many students in this class. Whenever you have an integer divided by an integer, you're going to have this problem. Even if it's a hard-coded, let's say a 4 divided by 3, that's going to resolve to 1, not 1.25. No, I'm sorry, 1.333.
If you want to separate the remainder, you can use the percent operator. This produces the remainder from integer division. So here's another example. We declare 3 ints, dividend, divisor, and remainder. And we initialize dividend to 5, divisor to 3, and then assign remainder the value of the expression dividend percent divisor. Now, 5 divided by 3 is 1 with a remainder of 2. The value of remainder becomes 2. This slide shows 2 examples of integer division and using the remainder function. 12 divided by 3 yields 4 with a remainder of 0, yet 14 divided by 3 yields 4 with a remainder of 2. When writing expressions, use spacing to make expressions more readable. Here's an example of 2 expressions, x plus y times z, and an alternative method, x plus y times z, with spacing. They're going to execute exactly the same. Remember, C++ for the most part ignores white space. So why not make it look more readable? Your order of precedence rules are the same as those in your algebra class. Remember, it was PEMDAS. Please excuse my dear Aunt Sally. Parentheses, explanation, multiplication, division, addition, subtraction. If you want to alter the standard order of precedence, you should use parentheses, because parentheses trump all other precedents. This slide demonstrates how to structure certain expressions in C++ that are mathematical formulas. And I'm not going to read these to you, but I suggest you take a close look at them. And you're going to be required to build, I would say, some moderate, not very complex, but not all very simple expressions in C++. Some expressions are used so frequently that C++ contains shorthand operators to make these sequences easier to type and more compact. The most frequently used arithmetic operator is the plus and a counter. where the counter gets incremented each time you run through a loop. And I know we haven't gotten to loops yet, but just trust me on this one. So plus equals. Let's cover that first. If each time you go through a counter, you're going to change the count and increment it 2, or add 2 to the count. Count equals count plus 2 can be written in shorthand as count plus equals 2. There's one for multiplication, there's one for division, and there's one for remainder. I'm not going to read them to you, but I suggest you take a look at them. These are very useful shorthand features of C++.
Chapter 2 is the most important chapter in this book, in this class. It develops many foundational concepts that will be built upon as we move forward in this class. Therefore, I'm spending a significant amount of time and effort on this chapter. I'm breaking the content for Chapter 2 into 2 sections. This is simply the first of 2 lectures for Chapter 2 because of its importance. Hope you've enjoyed it. Please do not hesitate to ask questions. I'm here to help you and to clarify any questions or concerns you have regarding the material. Thanks for watching. Have a great day.